My greetings, dear students. So in this lecture we will learn some applications of Fermat's theorem. So here the first numerical is, if GCD of a and 30 is 1, show that 60 divides a power 4 plus 59. So first of all we write the given statement in concurrence form, that can be written as a power 4 plus 59 concurrent 0 mod 60, and which may further be written as a power 4 minus 1 concurrent 0 mod 60, or further we have to prove a power 4 is concurrent 1 mod 60. So this is the desired numerical which we wish to prove. Next, we are given that GCD of a and 30 is 1. So from here, very easily we write the prime factorization of 30, that is 2 is to 3 is to 5, and very easily we can have that if a is relatively prime to 30, so it will be relatively prime to its prime factors. That is, GCD of a and 2 is 1, GCD of a and 3 is 1, GCD of a and 5 is 1. Now by Fermat theorem, so from here we have that 2 is a prime and 2 does not divide a. That means a power 2 minus 1 is concurrent 1 mod 2. And from here 3 is a prime and 3 doesn't divide a. So a power 3 minus 1, that is 2. 1 mod 3. And from here 5 is a prime, 5 does not divide a. A power 4 is concurrent 1 mod 5. Now you see, from here we get a is concurrent 1 mod 2. So raising power 2 on both sides, a power 4 is concurrent 1 mod 3. And here we already have a power 4 is concurrent 1 mod 5. Now just try to see, we already have this result, a power 4 is concurrent 1 here, and very easily we can raise power 4 here. And GCD of 2, 3 and 5 is 1. But when we multiply, we will get 30 only. But we need to prove this for 60. For 60. So we need 2 more multiples. So for that, we will do simplification here. First we square both sides. A square is concurrent 1 mod 2. Also a square is concurrent to, now 1 is concurrent to minus 1 mod 2. So from here you see 2 divides a square plus 1 and 2 divides a square minus 1. So combining these two, 4 divides a power 4 minus 1, which may further be written as a power 4 is concurrent 1 mod 4. Now name this 1, 2, 3. From 1, 2 and 3 we get as GCD of 3, 4, 5 is 1. So we get a power 4 is concurrent 1 mod 3 into 4 into 5. That is, a power 4 is concurrent 1 mod 60. So this is the desired answer. Next numerical, employ Fermat theorem to prove if P is on odd prime, this sum is concurrent to minus 1 mod P, as P is odd prime Therefore, GCD of A and P is 1 for all A lies in 1 and P minus 1. So, using this and applying Fermat theorem. First, for first number, 1 power P minus 1 is concurrent 1 mod P. Also, 2 power P minus 1 is concurrent 1 mod P. 3 power P minus 1 is concurrent 1 mod P. So we can write this as GCD of A and P is 1 for A lies in 1 and P minus 1. For every A lies in this. Similarly, that's why 1 power this, 2 power this, 3 power this, and so on up to P minus 1 power P minus 1 is concurrent 1 mod P. So once we have this, now to get the desired result, we will add all these concurrences. So by adding vertically, we will get 1 power P minus 1, 2 power P minus 1 up to P minus 1 power P minus 1, which is the desired left hand side. And what we get on the right hand side? 1, 1, 1, 1, 1. 1 plus 1, so on, 1 modulo P. And how many times this 1 will appear here? So this will appear P minus 1 times modulo P, which is further concurrent to minus 1 mod P. So we have 1 power P minus 1, 2 power P minus 1, P minus 1 power P minus 1 is concurrent minus 1 modulo P. In another numerical, statement is, assume that P and Q are distinct odd primes. Means their GCD is 1. Given P minus 1 divides Q minus 1, and also GCD of A and PQ is 1. Show that this concurrence holds. Now, as you know, as by earlier results, we will prove this concurrence for P and Q. Because they are relatively prime, the result will hold for their product. So let us start. Now, given GCD of P and Q is 1 and also P minus 1 divides Q minus 1. So by definition of divisibility, this implies Q minus 1 is equal to P minus 1 times K for K some integer. And also it is given GCD of A and PQ is 1. Now, as I already told, because of this, GCD of A and P is 1 and GCD of A and Q is 1. Now, employing Fermat theorem, as P is prime and P doesn't divide A power P minus 1 is concurrent 1 mod P. And similarly, Q is prime and Q does not divide A power Q minus 1 is concurrent 1 mod Q. Now try to see what we need to prove. We need to prove A power Q minus 1. So here in this part we are already getting that power. But how can we convert this P minus 1 into Q minus 1? So for that we use this relation. So we raise power K on both sides. That is, A power P minus 1 into K is concurrent 1 power K modulo P. And what is this? By that, this is A power Q minus 1 is concurrent 1 mod P. So this is number 1, this is number 2 from 1 and 2. As GCD of P and Q is 1, A power Q minus 1 is concurrent 1 mod PQ. Desired answer. Next numerical. If P and Q are distinct primes, prove that this concurrence will holds. So again, they are distinct primes. GCD of P and Q is 1 by Fermat theorem. So what we will get? So very easily, so we will apply Fermat theorem twice. Once we will take A is equal to P, and secondly we will take A is equal to Q. So here we get P power Q minus 1 is concurrent 1 mod Q, and second times we get Q power P minus 1 is concurrent 1 mod P. So this is how we will get this. Now we need to prove this result for PQ. So as in previous numerical, we will prove this result for P and Q. So you see, very easily we will have P power Q minus 1 plus Q power P minus 1. Now you will be surprised, how can we write this? But it is very simple. Why? Because Q is concurrent 0 modulo Q. So actually this is 0, we are adding 0. So similarly here, you see, we will write P power Q minus 1, Q power P minus 1 is concurrent 1 mod P. So again, from both of these two, we get P power Q minus 1, Q power P minus 1 concurrent 1 mod PQ. Desired answer.